Good morning everyone, I'm Giuseppe Laudani, a PhD student at Department of Electrical, Electronic and Computer Engineering at the University of Catania, and together with my colleagues, PhD student Giuliano Baiamonte, PhD student Gianfranco Di Martino, Prof. Michele Calì and Placido Calì, we have carried out work on a replacement methodology for lost wax casting in the production of bronze statues. The experimental part of the work was carried out at the Arts Laboratory of Sculpture di Calì, located in Sireale, Catania province. Investment casting began as a foundry technology for the creation of small parts, but thanks to the experience gained, the development of robotics and research into new materials, it's now possible to obtain casting weighing more than 150 kilograms from the investment casting process. Investment casting is a process based mainly on the lost wax casting technique and consists of a succession of highly specialized steps aimed at obtaining the required geometric and metallurgical properties. This method involves the use of a material with a low melting temperature, usually wax, to create the model. A mold made of refractory material is created around the wax, the characteristics of which must be such that it can withstand high temperatures and metallostatic forces. Thanks to recent developments in the fields of reverse engineering and additive manufacturing, investment casting can be optimized by reducing the time required to make the mold, through 3D scanning and 3D printing, and by using materials other than wax but with similar characteristics. In this work, we will deal with this new methodology, especially applied to the bronze casting process for the creation of sculptures, where the mold will be made through the 3D printing of the polyvinyl alcohol, PVA. The investment casting method, also known as an investment casting, is an ancient technique for making metal objects, dating back more than 6,000 years. The sectors in which its use are different, ranging from the production of automotive components to dentistry, from turbine blades to bronze sculpture. This process also offers flexibility in the reproduction of forms and allows for products that do not require further costly processing. In the field of bronze sculpture, where surface finish, complexity and dimensional stability are crucial, and this process is essential. The figure shows the current process used for the production of bronze sculptures: building clay model, wax and refractory material injection on the model, firing the refractory material and melting the wax at temperature of 900 degrees centigrade, bronze casting process. So, in this video is show the casting process. Bronze is melted at a temperature of 1200 degrees centigrade inside the crucible. Before casting, all impurities are removed so that the bronze is clear and flowing. After that, the bronze is lowered into the mold. The procedure of the proposed new methodology is illustrated in the figure. To be sure that the casting process works, it's necessary to verify that the refractory material used to create the casting solidifies within a shorter time range than the total solubility time range of PVA, as it consists of a mixture of gypsum powder, pottery and water. In this way, it's possible to immerse everything in water to make the PVA totally solubilized, and finally cook the refractory at a temperature of 900 degrees centigrade in order to delete all traces of water and impurities, in order to be able to immediately carry out the bronze casting. The choice of using PVA consists in the fact that the polyvinyl alcohol polymer is obtained through the partial or total hydrolysis of polyvinyl acetate. The resulting PVA is soluble in water but poorly soluble in organic solvents. The degree of cross-linking determines the amount of liquid absorbed and thus the physical, chemical, and diffusion properties of the polymer and ultimately its biological properties. PVA's resistance to organic solvents and its solubility in water make it suitable for many applications, including the textile industry, the production of paper products, the food packaging industry, and the medical devices. It's also widely used as an industrial and commercial product due to its low environmental impact, including high chemical resistance, water solubility, and biodegradability. The first stage of the new methodology is the 3D scanning of the prototype, and then proceeding with the 3D printing in PVA. It was decided to use this material, which is normally used as a support material for classing 3D printing, because it has the property of being entirely dissolved in water and therefore biodegradable. In this way, compared to the traditional methodology, the phase of melting the wax inside the refractory material in the oven at high temperatures is omitted, and environmentally sustainable methodology is used. Once the refractory was hardened, it was immersed in a tank full of water at room temperature for about 3 hours to completely melt the prototype PVA. Finally, the refractory was informed at a temperature of 900 degrees centigrade to remove any residue, and once it came out from the furnace, the molten bronze was poured, resulting in the final result. The bronze model obtained with the new methodology doesn't present significant aesthetic differences from the same model obtained with the old methodology. Therefore, it can be said that this methodology has been quite efficient and comprehensive. The advantages are many. First of all, PVA is known for its biodegradability in aqueous environments. This means that, if properly disposed of, it can be broken down by bacteria and other microorganisms in the environment. This is a significant advantage in terms of reducing environmental impact compared to many other non-biodegradable synthetic polymers. Secondly, 3D printing allows the uniformity of the thickness of the model, or at least the possibility of modifying the thickness of the model where deemed necessary. Finally, there is the advantage of omitting 2 steps compared to the traditional model, allowing considerable time savings. On the other hand, in order to have an excellent quality of the model to be reproduced, it's necessary to use 3D scanners with very high resolution, entailing an higher economic expense. In addition, it's necessary to have 3D printers that can print models made entirely of PVA. Another economic disadvantage is in the purchase of the reels of the latter, since it's not very low cost. Ultimately, PVA 3D printing offers significant benefits in terms of biodegradability and the use of renewable resources, but it's important to adopt practices and technologies that maximize the efficiency and sustainability of the overall process. This includes optimizing print parameters, managing vast materials responsibly, and disposing of print residues appropriately. Thank you for your attention.